Our project is comprised of 5 modules, namely Accident Avoider, Navigator, Sign Recognizer, Accident Detector and Voice Commands. Accident Avoider has object detection, for which we are using an object detection model that is trained on COCO dataset and converted to TensorFlow Lite backend in order to optimize its performance without losing too much accuracy. To run object detection on the Android device, we are using TF-Lite library as it is optimized for inference in mobile and embedded devices. Distance from the detected objects is being calculated using focal length of camera, perceived width of object and known width of object. We have set known width already according to the respective objects such as car, truck, etc., while the perceived width is calculated using pixels acquired by the object in the image. Warnings are displayed when the distance from the detected objects falls below a certain threshold value, which we calculate considering the reaction and braking time. Its formula is being shown on the screen. To detect lanes, first we have to resize our image to 300 by 300 so that there will be less computation to perform. Then we find the edges in our image, for that we convert the image to grayscale. Later we isolate white and yellow colors in HSV color space, as they are the colors for the lane on the road. After isolating the colors, we apply canny edge detection to find edges. Now that we have our edges, we apply a perspective transform on a quadrilateral area which is represented by a red shape in the image at the left shown on the screen, so that we would get a bird's eye view of the region of interest. Now to detect the lanes that are the left lane and the right lane, we have to find the starting point of both these lanes. To find the starting point of each lane, consider the image as shown on the screen at the right. In the image we can see that it is now divided into 3 parts. The upper part is ignored, and we are then left with 2 parts below. The part of the image at the left represents the left lane, and similarly, the part at the right represents the right lane. Now for each part we have to first calculate the histogram, that is, we move from left to right on x-axis and sum all the pixels values in the y-axis corresponding to the x-axis position or index that we are on as we move. Now that we have a histogram, a good starting point of the lane would be the x-axis position or index with the greatest sum. Now that we have our starting points, we will move through the explanation of the algorithm only at the right lane, and the same steps will be followed on the left lane. Then we will move a sliding window in the y-axis from bottom to top. And the first x-axis position is the starting point of the right lane that we previously calculated. The first position of the sliding window is shown in the middle image. Now, the sliding window will move in the y-axis with fixed intervals. But it will move in x-axis such that it follows the lane. On the rightmost image, we see the enlarged version of the sliding window. Then in the sliding window, we average the x position or index of the non-zero pixels, and we chose that average as the new x position or index of the next sliding window. We will follow these steps on each lane until the sliding window reaches the top of the image. After following the previous result, we will get the points visualized by the sliding windows in the image as shown on the screen. Lastly, we unwrap these points by first applying the inverse perspective transform, then again apply a transform to resize the points from 300 by 300 space to the original image height and width. The result is shown in the image on the screen. For accident detector, accident is being detected using certain diagnostic trouble codes generated by the OBD2 of car, which are triggered by the airbags in case of an accident and received by our application, which waits for them to be received via Bluetooth. In case of navigation, we have used Google Maps API for displaying the map on the screen. Furthermore, we have used Places API by Google to get auto-suggestion in search bar when choosing start location or destination. Moreover, we have used Directions API, which returns a JSON object between 2 locations provided using a URL, and then we have used the information placed in the JSON object to provide the user the directions visually and audibly at each point necessary. For sign recognition, we have used a TF-Lite model to detect traffic signs along the road. Later, we passed the cropped image of the detected traffic sign to a classification model to classify the traffic sign that we have trained on German traffic sign dataset and later converted to TensorFlow Lite for optimized performance. In the end, for voice commands, we have taken help from Voice Commands API provided by Google in order to detect and translate the voice commands provided by the user. Finally, we would like to thank you for patiently watching this whole video. I hope we were able to provide you a brief understanding regarding the technical details related to our project.